Hi, everybody. Okay, so we're going to wrap up this discussion of equivalence relations with, I think, what is maybe the most fundamental important example, of, at least in abstract algebra, of how an equivalence relation gets used. And we're going to revisit, again, something we've seen many times, which is congruence on integers. And now we're going to give a formal definition of what are called the integers modulo n, using equivalence relations. So here's what I mean by a formal definition. We're going to fix a natural number greater than 1, and we're going to define a set written Zn, the integers modulo n, and we're going to define this set to be the collection of equivalence classes that are created by the equivalence relation A is congruent to B mod n. In other words, Zn is the collection of equivalence classes A, here A is in Z, where more formally A is the collection of X in Z such that X is congruent to A mod n. Now, for what I'm about to talk about, there's a careful walkthrough in the book of the case n equals 5. So I'm not going to spend too much time on concrete examples, but I just want to remind you that this equivalence class is an arithmetic progression. And we've seen this now several times. So for instance, if n were 5 and a were 2, then the equivalence class of A would be the arithmetic progression starting at 2 and going in steps of 5 in both directions. And so the integers mod n as a set, the elements of the integers mod n are themselves sets. But those sets form a partition by our discussion before. So each of the sets, altogether, the sets cover the integers, and they have no elements in common. So the first thing is to just recall or reprove or restate the fact that Zn has n elements. So the equivalence classes under the congruence mod n relation partition the integers into n classes. And the proof of this is the division algorithm. Every integer in Z can be written in only one way as, let's call the integer A. A equals Qn plus R, where R is bigger than or equal to 0 and less than n. So in other words, when you divide A by when you divide A by n, you get a quotient of Q and a remainder of R, and the remainder R is between 0 and n. Notice that, therefore, every integer A is congruent mod n to exactly 1 R between 0 inclusive and n minus 1 inclusive. And that's because from this formula, you have A is congruent to R mod n. And R is between 0 and n. And so this shows that every integer is congruent to at least one of these things. And on the other hand, if A were congruent to J mod n, and J were between 0 and n, then that would mean that A was equal to kn plus j. That's what this congruence means. It means a minus j is a multiple of n. And so j would have to equal r and k would have to equal q, because there's only one way to write a as qn plus r. So this tells us that Zn is partitioned into n equivalence classes, and each equivalence class corresponds to a possible remainder when you divide an integer by n. And those possible remainders go from 0 up to n minus 1. Those remainders are unique, so every integer belongs to exactly one of these n equivalence classes. And so the integers are divided up into these classes. One way to think about, if you wanted to see this, you could write the integers like this. Let's say n is 5, just for the moment. You could write 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And I guess we could count down as well. You'd have minus 5, minus 4, minus 3, minus 2, minus 1, and so on. And then you see that by looking in the columns, you've got the integers partitioned into these 5 classes. This would be the class 0, 1, 2, 3, and 4. So when we've talked about the integers, okay, maybe I'll just stop talking there, but let's go on to the next step. This wouldn't be that interesting, except that we can now define arithmetic mod n, or arithmetic in Zn, using these equivalence classes. And we do this in the following way. We define the sum of two equivalence classes to be the equivalence class of the sum. And we define the product of equivalence classes to be the equivalence class of the product. So if n were 5, for example, this would say that 2 plus 1 is 3. No problem there. A little more mysterious would be 2 plus 3 equals 5. Notice here that I'm writing equals. I am not writing congruence. I'm just writing equals, but I'm working with equivalence classes. So this formula comes from the fact that by definition, the equivalence that we define 2 plus 3, we take the sum of these 2 and 3 and we make that equivalence class. How does this make sense? Well, we're working modulo 5 here, and 5 is not one of our standard equivalence classes. Remember, the equivalence classes were 0, 1, up to 4 if we were working mod 5. Except that it really is, because the equivalence class of 5 is actually the same as the equivalence class of 0. Go back to this picture here. All of the multiples of 5 are in a single equivalence class. So in working with equivalence classes, you get what you would call modular arithmetic. Instead, but the things that you're adding become equivalence classes. So for example, if I were to do 4 plus 3, I would get 7, but 7 is the same as 2 because it only depends on the remainder when I divide by 5. And this is how you define addition on congruence classes. And you define multiplication similarly. You would say that 3 times 2 is 6. But the equivalence class of 6 mod 5, this is mod 5. The equivalence class of 6 mod 5 is the same as the equivalence class of 1 mod 5. Because again, the remainder of 6 when you divide by 5 is 1. And so when we multiply these equivalence classes, we can always get, no matter what it, if I were to, no matter what it looks like here, I can always convert my equivalence class back to one of my standard equivalence classes. This is all worked out in detail in the book for n equals 5, and you should read it. And I just want to highlight what is the possible pitfall of this. What could go wrong? Well, what could go wrong? There are a lot of things that could go wrong, but the main thing that could go wrong is what's called the issue of being well-defined. because these things have different names. So let's look at an example. Suppose I wanted to work, let's suppose n was 7 for the moment, and I want to add 3 plus 2 working mod 7, and there's no problem. That should be 5. And remember that the equivalence classes mod 7 are 0 up to 6. Those are our standard equivalence classes. Those are their, and so that looks okay. But remember that 3 is the same as the equivalence class of 10. And 2 is the same as the equivalence class of minus 5. Well, or let's use, let's not do that one. Let's say it's 2 is the same as the equivalence class of minus 12. So if I add 10 and minus 12 together using this rule, I get minus 2. And you might be a little worried here, except that actually this all checks out because 3 is the same as 10 and 2 is the same as minus 12. And actually 5 is the same as minus 2 mod 7 because remember that these equivalence classes are just the arithmetic progressions, and the arithmetic progression for 7 that starts at minus 2 is the same as the arithmetic progression for 5. It goes minus 2, 5, 12, and so forth. If I've done this correctly. So even though these congruence classes may have sort of different names, you might be able to rename 3 as 10 and 2 as minus 12, and then you would get a different, looks like a different sum. In fact, you get the same sum. And that's what it means to say that the addition is well defined and that the multiplication is well defined. This may seem strange, but it's not as strange. There's actually another situation in which you're very used to this, which is the case of fractions. When you add fractions, you first typically put them over a common denominator, which is to say you pick another name for the same fraction. Then you add them. Then you put the result into lowest terms. And if you think about fractions as equivalence classes of pairs of numbers like we did earlier, then it's a similar situation where you have to use different names for the same equivalence class in order to do a calculation. So let me just indicate why this all works out for addition. So what we want to show is that suppose that A and A prime are the same equivalence class. Here we're going to fix n. I'm not going to say what it is, but fix n. And suppose that B and B prime are the same equivalence class. Well, what does that mean? That means that A is congruent to A prime mod n. So A equals A prime plus Kn. And B is congruent to B prime mod n. So B equals B prime plus Sn. Here K and S are integers. And now A plus B is equal to A prime plus K prime plus K plus S n. So A plus B is, not K prime, B prime. A plus B is congruent to A prime plus B prime mod n. And therefore, whether you use A and B to compute A plus B, or you use A prime and B prime to compute A prime plus B prime, even though the answers may look different, they're actually the same. And so in this way, the collection of equivalence classes of congruence mod n allows you to do addition and multiplication on them. And in this way, you get arithmetic mod n in a very abstract and natural way.